All right, guys, so this is number 24. From information on this book, compute the radial acceleration of a point on the surface of the Earth at the equator. Oh, the radial acceleration at the equator. All right. Owing to the rotation of the Earth around the axis. So let's just find the radius of the Earth. So the radius of the Earth, we're going to find that value. And what else do we need? The time it takes for the Earth to go around. So, like, if this is the Earth, if you're at the spot of the Earth, and let me redraw this. Let me concentrate here. There we go. I'm a bit high right now, but that's all right. So this is going to be the Earth, and we are going to compute the what are we doing? Oh yeah, the radial solution. Oh my god, I'm having a short-term memory at the moment. Okay, so this is going to be the radial, pointing this way in this direction towards the center, and we're at the equator, and we are going to go around of the Earth. We're going to take that distance or that position or that distance that it travels really, and we're going to divide that by the time. So what time it takes, folks? So the time is going to be 24 hours. Beautiful. We're high levels of IQ here. So the radius of the Earth, folks, is going to be 6378 kilometers. Oh my god, I'm 6378 kilometers. Beautiful, folks. That's very beautiful. So that's going to be the radius of the Earth. And what we're going to do is we're going to take 2 pi times the radius divided by the time it takes to go around the Earth. You could try and do it in sidereal days to get a little more accurate if you want, but I don't really care. So 6378 times 10 to the 3, and it's probably better if you do use sidereal day because it doesn't actually go. It doesn't actually go around like 24 hours. It goes a little extra distance or something like that. I don't really know. But we're not going to get worried about the... why am I ranting here? Oh, yeah. Anyway, so this is going to be 2 pi r divided by the time. So once you get that, you're going to get the speed. So the speed is going to be 1159.55. That's way too fast. There's no way it's that speed. Oh my god. Once you put this in the calculator correctly, the speed should be 6.3, whatever the fuck. Okay, 82 meters per second. So there you go, folks. So that's very beautiful. I'm going to start in this speed. Okay. So why do I need the speed, folks? Because we're going to measure the radial acceleration. So think about an object. You're standing at the equator, and the Earth is indeed flat because it presents itself flat. There's no proven of the curvature radius, even though there actually is. So whatever. So you're on the Earth is flat and you're standing at the equator, and gravity's pushing you at 9.8 meters per second square. But gravity is not proven, so therefore the Earth is flat. So once you get, so technically there's already a radial. Wait, does it take account to that? Compute the radial acceleration of a point on the surface. The radial acceleration. Well, I guess your minus 9.8. That I'm not going to worry about gravity. I'm just going to pretend that gravity doesn't exist, and as it's rotating in a circle, especially light. Light is a very interesting phenomenon, folks. I'm such a weird fuck. I'm sorry, guys. So this object gets pushed away as it goes around. So as it goes around the circle, as it rotates around the circle, it's going to want to be pushed away. And why is that? Because of Newton's third laws of motion, because there's an outward acceleration. And that outward acceleration is going to equal to what's in the inside of the acceleration. Ignoring the effects of gravity, of course. So that's basically what we're finding, folks. We are going to take the radial derived by the formula, where this formula, remember how you guys derived it? You took the angles of the 2 speeds, and this angle right here of the change of the radial, which is basically this vector and this vector, and And what's amazing about this angle is that they're the same as the angle here. So let's just blow this out. So this is going to be S or radius 1 and radius 2. This is going to be the V1, V2. If you align this angle to be V2 right here, they're the same angle. Because they're the same angle, you can work out the mathematics of this to get the V squared over R. That's very beautiful, folks. So this is going to be, because there's the same angle and these distances are the same, you can use a bit of, like, I don't know, geometry to figure this out. That A equals V squared over R. So therefore, once you figure that out, then you know that this tangential speed would be, this is the radial speed. This is the centripetal acceleration that I haven't talked about. But that centripetal acceleration is when you have the tangential speed square, you take the radius, you get that A radial. So since we already found what the tangential speed is, which is really just the 2 pi r times the t, that's the tangential speed. That was the whole point of this, to get that value right there. Now we're going to take the V squared divided by the radius of the Earth. So I'm going to store the radius of the Earth in my TI-84 calculator. I already did that. There we go. Everything's stored there. So I'm going to take V squared divided by R. And that radial acceleration is going to be 0.03373033 meters. So basically so this is going to be 3.37 centimeters per second squared, since the Earth is indeed flat and there's no such thing as gravity. That's how much you would fly off realistically. So all right, folks. So basically what I'm trying to get at here is that you know, if the Earth was indeed flat, which is not, you would be flying at that speed. I'm an idiot. The acceleration, you'd be flying about that. And however, you have to take into the account that gravity is a real thing, and you do indeed fall at 9.8 meters per second square, because the laws of nature will always be existent, regardless if humans exist or not. So therefore, this right here, folks, this is the acceleration, the centripetal acceleration of the Earth. So so it'd be 9.8 minus so we just found, so the centripetal acceleration is this. It's actually because we are being accelerated towards the ground, we take into account 9.8 minus that. So it's actually, the true value is 9.8 minus that. That would be, even though I didn't really store this, 9.76 would be the realistic radial acceleration of this thing. Anyways, folks, I know I'm ranting, but I hope you guys enjoy this.